Okay, here we go. So last time we were talking about this kind of novel idea of taking our various different coordinate systems, polar, cylindrical, spherical, reminding ourselves that we observed previously that you could view those as functions, and now taking this sort of like unusual idea of let's choose to view them as change of variables functions. Seems like an odd choice, but we can certainly do so. It's a free country and all that. So we've already talked about the stretching factors and the choices on the coordinates that allow you to avoid the absolute values, and we're ready now to actually implement this and go ahead and actually use polar coordinates we're going to start with, that is, as a change of variables function. Okay, so we're going to start then with a not that bad looking domain over here in the XY plane. We're going to do a double integral over this region here. And how would that work out? Let's first take the brute force approach, see how that would work out, and the answer is not well. The point is that this curve right here, right, being as it is a curve, you'd have to solve for either y as a function of x or x as a function of y, and that makes this square root show up in your inner bounds, which means that square root's going to show up in your outer integrand, which means when you get around to doing your x integral from 0 to 1, you're going to have a nasty integral on your hands, and mostly as a result of the shape of the domain here, which is not nice in rectangular coordinates. Okay, so let's actually try to avoid this. We're going to avoid this with using polar coordinates, again, as a change of variables function. And here's what I claim. I claim to start off that this rectangle is the pullback domain. So in particular, if I were to take this and look at its image by way of the polar coordinates function, I claim that we get this given initial domain. Okay, is everybody on board? Is everybody happy? Okay. All right. So, all right, now let me try to persuade you that this is the case, that this really is the pullback domain. Let's look at this edge right here. This edge has theta equal to 0. Right? And then on that theta equals to 0, we have r going from 0 to 1. What does that look like on the xy plane? Well, theta equals 0. R goes from 0 to 1. There it is. Right? Just interpreting polar coordinates on the xy plane. Let me leave that there. Now let's look at this edge. What can I say about this edge here? Well, notice on that edge, r is always 1. Which means we're somewhere on the unit circle, but more to the point, we're on the unit circle where theta goes from 0 to pi over 2, which means it's actually just this part of that unit circle. Okay, then let's look at this edge right there. That edge has theta equals to pi over 2. R goes from 0 to 1. Which is that, again, just interpreting polar coordinates on the xy plane. And then now the weird one is to think about this edge here, this left edge, and it's tempting to think that the image of an edge should be another edge, right? But in fact, if you think about it, this entire edge has r equal to 0, and r equal to 0 means just the origin. No matter what theta does, r equals 0 puts you at the origin, right? So kind of a weird way that the mapping works, but nevertheless, that rectangle maps into this, whatever you call that, quarter disk, I guess. How are we doing? Is everybody happy? Okay, so we're in business. This integral that was initially given over here on this, again, I'm going to say undesirable domain, right? I can pull it back, pulling back through the change of variables function, and our new domain is a rectangle, and of course everybody likes rectangles. So this is our pullback, and we're mostly in business at this point, and we can just kind of matter of writing things down at this point. We've got r and theta, easy bounds. After all, it's just a rectangle. Look at the rectangle. There you go. Okay. Don't forget that area in the XY plane, we've already computed the stretching factor. Stretching factor is r, so dx dy becomes r dr d theta. Then there's the matter of the integrand, this x squared plus y squared, and of course that's just an easy rewrite. That's just r squared. Okay, so all together then, notice that my integrand is r cubed. Now this is actually a kind of a sticky wicket stumbling block for a lot of students. A lot of students put the r here next to the dr d theta, rightly so, but then kind of feel like not only does it need to be there, maybe that it needs to stay there. And then keep it separate, like it's just, you're not allowed to do anything with it, and like this is your integrand. Now, that's just not true. The whole point of a stretching factor is that it is supposed to become a part of our new domain. So don't forget to not only insert the stretching factor, don't forget to actually absorb it in and actually make it part of your new integrand. So our integrand is r cubed. The antiderivative is 1/4 r to the 4th, and it's all single variable calculus from here, and easy single variable calculus at that. So nice, easy answer. Notice no square roots at all anywhere on the left. Massive square roots and pain, associated pain, on the right-hand side if we had done it in rectangular coordinates. Is everybody with me? Okay. Right. Okay, so now I'm going to give you a different point of view on this. This is just a different way of thinking. What we did in the previous example, coming back up to it, is we took our given domain and we I'm going to say we pulled back the domain to get ourselves a new domain. And then we sliced up the new domain in the usual way. We have our r slices and our theta slices. So the observation I want to make next is that instead of pulling back your domain, another way you can kind of think of this is you can literally push forward the slices themselves. We can ask, what does it look like when I'm doing slices of, this pullback domain? This what does a theta slice look like over here? And then ask, what does it look like over here? And then I don't have to draw a new domain at all. Let's see this in action. Here's what I mean by slices. Of course, for example, these are theta slices. By theta slices, of course, I mean constant values of theta. So those are theta slices. Well, this is what those look like over here. So again, rather than pulling back the domain, I'm pushing forward the slices. So I can do this kind of slicing of the pullback domain, no problem. I can also do this kind of slicing of my existing given domain. Okay. Ditto for r slices. Constant values of r look like this. So those are r slices. Well, constant values of r in the xy plane look like that. So all of this in mind, here is a reconsideration now of the exact same example that we did a second ago. Again, previously we took our given domain and we reverse engineered, we pulled back and found our new rectangular domain over here, which we then did slicing business in the r theta plane. Again, we're not going to do that. I'm going to leave this visible. You'll see I have it scratched out. I'm going to leave it visible, right, so that you can, just as a reference point, kind of compare and contrast, but we're really not going to use that over there at all. I'm just going to say, okay, well, here's my domain, and if I want to know the range of values of theta, which, again, not to be fair, range of values of theta, looking at theta slices, technically it's happening over here, but I don't have to look at it, or I don't have to see it over here. I can see the theta slices, and thus the range of values of theta over here. Here's what my theta slices look like. There's my first one. Here are various other theta slices. And there's my last one. And you can see right here in this picture, no new picture at all. Theta goes from 0 to pi over 2. That's the exact same answer I got when I was looking in the r theta plane, yes.
Can you just quickly show us how you got the scaling factor of r?
Oh, so that's that was from last time. That's you take your change of variables function and you plug into the Jacobian determinant formula and yada yada yada. Right, that's a computation. Okay. Right, and then the Jacobian determinant is r. And you got to worry about absolute values and all that jazz. Punchline. Yeah. Okay. Is that cool? Is that okay? Yeah. Okay, so there's our theta range. Now, proceeding as we usually do with theta fixed. Now we ask, what's the range of values of r? Well, what do our r slices of our theta slice look like? Well, of course, r slices are like this. Keep in mind, I'm only interested in the r slices of the theta slice. So in practice, really, I'm just kind of moving from this starting point to that ending point. And again, pretty easy to read right off the picture. Clearly, missed. Starting with r equals 0, ending at r equals 1, because of course it is a unit disk, so that radius is 1. Everybody on board? Okay, so now we get the same exact answer we did on the previous page. What's the point? Again, the point is I didn't have to draw a whole new picture. Right? Implicit, yes, of course, I am doing a pullback. I am doing a change of variables. Yeah. I just don't have to draw that. So, a lot easier to see on this picture. Okay, now let's see a bunch more examples of this. We're going to see a bunch of examples of polar coordinates, and then we're going to keep on with a bunch of examples in cylindrical and spherical. Here we go. Integral in the xy plane. The domain is, let's see here, our domain is this unit disk right there. Obviously, rectangular is suboptimal. We're going to have square roots. It's going to be annoying, so we don't want to do that if we can avoid it. So let's ask the question. Okay, well, how do we slice this up? D theta. What do theta slices look like? Well, here's our first theta slice, arguably, and then our theta slices kind of proceed along. And I'm just going to shorten that as well. It goes all the way around. And now there's a temptation to say, well, my last theta slice is in the exact same place, and if it's in the exact same place, shouldn't I call my last slice 0 also? That's an illusion based on the fact that, of course, this is in the xy plane. The actual pullback domain is in the r theta plane. And as I do these theta slices, theta is increasing the whole way around. So if I start with theta equal to 0, having made a full turn, I have to call my ending theta equals 2 pi. Is everybody all right with that? So, good rule of thumb, nice, easy fact to remember. If, in fact, your theta slices go all the way around, if your solid envelops the origin, right, then 0 to 2 pi. Nice, easy answer. Apply. It happens a lot. Okay, so then we pick an arbitrary value of theta. Now we move on and ask what's the range of values of r. Well, okay, our r slices start there, where clearly r is equal to 0. And our r slices end there, where r is clearly equal to 1. Again, this is a unit disk. What do you think? Everybody all right with that? All right. And then, single variable calculus ensues and answer. So no problem. Also, you'll notice in this ensuing calculation, no square roots. Really nice, easy calculation wasn't even any trig. I mean, it's really nice. It's a much more desirable than this, which would have been a drag. Okay. Alrighty. A couple tips and tricks, things to keep in mind. As it turns out, drd theta. I hesitate to say always, but I mean, for all intents and purposes, practically always, this is the order that you should put your differentials. I have in the past gone to some trouble and thought up a highly unnatural, manufactured example of one where d theta dr is actually a little bit nicer. It's extremely unnatural. It's almost certain you're never going to encounter such a thing. So with the asterisk that the rare exceptions, just do drd theta. You really don't need to entertain doing it in the other order. This is always best. Okay. All right. Next. There's a really dangerous little landmine involved in these kinds of calculations. We can look at this as an example, by the way. We draw this picture and we start thinking about various kinds of slices and ranges of values and starting and ending, etc. And we are so focused very often on what our bounds are. It can be really, really easy to accidentally forget to put in the stretching factor. You'd be surprised how easy that is to do. And I don't have actual numbers on this, but anecdotally, many years experience of teaching this in equivalent classes, it happens a lot to students on exams, and they forget to put in that stretching factor. It's a really big deal too, and the thing about it is, you have to keep in mind when exams are being graded, I have to grade it based on what's written on the page, right? I can't. Oh, well, the student didn't put in the stretching factor, but I feel like they probably understood that. I can't, right? So I have to grade based on what's written on the page. Give me just 1 second. And again, it's a big deal. The stretching factor is the most sophisticated idea in all of this change of variables stuff. So it's unavoidably worth a lot of points, and it's, again, easy to, oops, I forgot, accidentally leave it off. So, very dangerous problem, and I'm coming back to you in just a second. I have a helpful suggestion for how to avoid oopsing this, and that is that when you write your differentials, drd theta, write down the stretching factor at the same time. View these as being a single thing, which, by the way, this is dx dy. This is your dA. This is what we call your area element or your area differential. So write it all together all at the same time. Again, very, very natural, but a great way to prevent yourself from accidentally forgetting that R. Yes, sir.
Is R, or is the stretching factor always R?
Well, yeah, that's what we proved last time with this calculation here. And again, with the small price that we have to always choose non-negative values of R, yeah, the stretching factor is always, gotta love it, always R.
Do we still have to show that? Right?
Nope. That's established. Unless the question hypothetically says show that the stretching factor is, or compute your polar coordinate stretching factor, something like that. Then yeah, of course. But other than that, you may remember. In fact, you really should. Everyone should memorize this stretching factor, and feel free to use it for free. Right. Okay. So again. This is just a tip. This is not a requirement, but I think it's really good advice. Always write this down all at once. You should get the willies anytime you find yourself writing down just drd theta, and that's it. That should feel super creepy and weird to you. Right? That'll help. Okay. Lastly, we have the same sort of strategy for how to identify bounds. Just understand that where they come from certain points that you can identify as being on certain curves, which you can understand with certain equations, which you can then solve for the bounds you're interested in. Okay, just like with everything else we've ever done. Okay, another example. This is interesting in a couple of ways. We're going to be interested in an integral here on this annulus, which is this ring-like thing here. I like to think of it as being a moat around a castle. I don't know. I find that fun. So maybe this integral possibly might be computing the volume of water in the moat, whatever, right? So how would we compute this integral? A couple of different approaches we could take. Here's the first thing you might try. A clever thought would be to say, well, first, I'm going to compute the integral on the entire yellow region. And then I'm going to subtract the integral over this orange region, and yellow minus orange would give you the moat. Okay? We do this kind of thing in other circumstances. Seems reasonable. Seems like a good strategy. And depending on the circumstances, it could have been, but not here. Because look at our integrand. Our integrand, basically 1 over r, is undefined at that point. It's undefined at the origin. And it's not just sort of like barely undefined. It's wildly undefined, right? The function's exploding at the origin. Right? So neither one of these integrals makes any sense as we've defined double integrals so far. So this just does not work at all. Is everybody on board? Everybody see the problem? Side note, you may be thinking to yourselves, oh, this reminds me, we did something just like this in Calc 2 with improper integrals. Everybody remember improper integrals? Way of kind of avoiding and yet approaching problem points, right? And couldn't we do something like that here? It turns out that's a stickier business than it might look like. With multivariable, it's just that's awkward and we're not going to do that. So we can't do it. So that approach stinks. Okay, fine. Rectangular coordinates it is. Well, bad news there. Of course, you have to chop up your domain into 4 separate pieces. That's no good. Right? Who wants to do 4 separate integrals? Which, by the way, you'll notice each one of these 4 separate integrals, square roots in your bounds. So this is not just 4 integrals, this is 4 undesirable integrals. Also, not good. Look how easy it is in polar coordinates. There's nothing to it. In polar coordinate, where did my, okay, here we go. In polar coordinates, notice that theta just goes all the way around. So theta goes from 0 to 2 pi. Nothing to it. For a given value of theta, now let's fix a value of theta. What's the range of values of r? Well, r starts at that point, which is on this curve, which has this equation. So our lower bound is 1. Okay. And then for the upper bound, well, the upper bound for r is at this point, which is on that curve, which has that equation. So my upper bound for r is 2. What do you think? Everybody see how that worked? Okay. So our integrand, of course, we've got to deal with that. Our integrand is 1 over that square root, which conveniently is just 1 over r. Again, a little scary. We see that 1 over r, we think, well, yeah, but don't we have a problem here? Isn't this going to explode or something? Actually, for one thing, it's not even close, because check it out. R doesn't go anywhere near 0 in this integral. I'm not going anywhere near that problem point. So, for one thing, we have no concerns at all. Right? And secondly, when you put your stretching factor in there, and again, remember, don't ever write dr d theta without writing down r dr d theta. Right? I want to make sure not to forget that stretching factor right there. But notice that fixes our integrand anyway. We don't even have a fraction. This integrand is actually just 1. So this is a super easy iterated integral, and boom. How's that? Is everybody happy? All right. Okay. All right, here's a harder one. So this says we want to look at this region here. Well, wait a second, not exactly. I want the points that are in that region that are not, this backslash means exclude, right? I want the ones that are not in this region, that being this purple right here. So I want the part of the blue region that is not in the purple region. And so that, of course, no problem, just gives you this gray shaded region that we have right there. So let's let that be our domain, right? This is what we're doing our integral over. This region right here is kind of solar eclipse looking thing. And by the way, you could do this in rectangular coordinates. Notice though that either way you slice, dx dy or dy dx, take your pick, you're going to slice through corners and such, and either way you do it, you're going to have 3 separate integrals. That's already bad. Even worse, they're going to be separate integrals that have square roots all over the place. This is no fun. Nobody wants to do it that way. Okay. All right, so we're going to do this in polar coordinates instead. R d theta, again, very important. Nice little hack for remembering your stretching factor of r. Please, cannot emphasize enough, do not forget your r. So, yeah, don't forget that r. Let's see, our x, that was easy. That's r cosine theta, old news. And so we just have to figure out the bounds. So let's talk theta bounds first. Theta slices look like this. Right, so where's the first, where's the last? The first slice is going to be this point down there. What can I say about that point? Now, you have 2 different ways that you can do this. You can write down that equation and that equation and solve for theta. That's not even all that bad. If you want to do it that way, you could, again, write down those 2 equations, solve for theta, boom, that'll be an answer. Let me show you the trick way to do it, though, the easy way to do it. And that is to observe that this point, keep in mind we're interested in this point, is part of a very convenient little triangle, 2 of the edges of which, you'll notice, are radii of this circle, which has radius 1. So these 2 lengths here are both 1. That's just a little geometry observation there. But then here's the other thing. Notice that this edge is a radius of this circle, which also has radius 1, and that means that this edge has length 1. So with all of that noted, check it out. I have myself here an equilateral triangle, and y'all remember the trig of equilateral triangles, or I guess not even trig, geometry of equilateral triangles, and that instantly tells me that this angle that I'm interested in, this angle here, is just negative pi over 3. Everybody see how that worked? It's a nice little time saver. Be surprised how often little clever little tricks like this come up. Good to know. Good to be on the lookout for them. So I hope you'll be on the lookout with this in mind. Alrighty. Ditto, by the way, for this point up here, there is a similar equilateral triangle that you can persuade yourself of, and again, that makes this pi over 3 for this angle. All right, now on to the R bounds. We're going to fix a value of theta. Here's a theta slice, arbitrary theta slice there somewhere between the bounds that we just talked about. Where does R start? Well, R starts at that point, which is on this curve, which has this equation. The lower bound for R is no problem. It's just 1. Now let's think about the upper bound for R. We just did the lower bound for R. Let's think about the upper bound for R. Upper bound for R, this point, which is on this curve, which I claim has this equation. Now, we've got to think about where this equation came from. It's not that big a deal. It wasn't given, but you can infer it from the fact that this has a boundary curve whose equation is just this right here. It just make this an equal sign. That gives you that boundary curve. And taking that rectangular equation and converting into polar coordinates gives you that. And keep in mind, we're interested in solving for r because we're looking for an r bound. So this r is 2 cosine theta. How we doing there? Everybody buy it? Flashbacks to chapter 1, by the way, right, where we took rectangular equations and converted to polar equations, and you remember it's really just a matter of plugging in the conversion formulas and doing some algebra, right? But make sure that you're proficient with that. Make sure you can crank stuff like that out quickly and reliably. Okay. All right. So, yeah, we're in business. And our integral is just this, and it's not that bad to crank out. Yes, there is some trig in there. You could make the point that this other, doing it in rectangular coordinates, well, yeah, it had square roots, but at least it didn't have any trig in it. True. And this has got trig in it. But given my choice, between an integral with trig in it and an integral with square roots in it, I'll take trig every time. Because we have trig identities. And trig identities just give you a lot of flexibility and a lot of options, and things just work better. There might be an exception somewhere, but in all my years as a physics major long ago, I'll take trig every time over square roots. Okay. All right. Okay, moving along. All right, now this next one is a little bit of a weird calculation. This is historically interesting. This goes back a couple hundred years. Very clever calculation. First, let me try to persuade you why we care about this. Y'all may have had a class in probability, or you may not have. If not, you should have had a class in Calc 2. That Calc 2 class may have talked about probability a little bit. Anyway, either way, when you want to use something called a probability density function to compute a probability, you do it with integrals. Excuse me. And the integrand is your probability density function. This particular one is known sometimes as a normal distribution or a Gaussian distribution. And it is not an arbitrary thing. This is very natural. It comes up literally in the physical world, comes up in biology all the time. And ultimately the reason for that is because it comes up and it, oh my gosh, excuse me. I think it's all this chalk over here or something. It comes up because of a very significant mathematical result that involves, what happens when you have any distribution at all, any distribution, and you sample it a bunch of times and then average your results. And it turns out that in the limit, everything approaches normal distributions. It's a very powerful, very important fact in probability. So anyway, very important thing to want to take an integral of. And yet, you may recall I mentioned effectively this fact a little while ago. There is no what we call closed form, aka convenient antiderivative. For this function, you just can't do it. There's nothing you can write down that is an antiderivative unless you venture into summations and stuff like that. So we are in a bind here. We want to compute this integral. We need to compute this integral, and the fundamental theorem of calculus is not helping. We don't have an antiderivative. So here's the move. Very slick. Wish I thought of this. I think a lot of mathematicians wish they thought of this. This is super, super clever. step one, give it a name. We're going to call this J. Whatever. Step two, let's write down J squared. Now, I claim this is J squared. After all, that's J, and I claim that this too is J. If you think about it, this in fact is exactly the same expression. I'm just using a different dummy variable. Whatever, it's just a dummy variable. Who cares? Right? There's nothing magic about this particular letter of the alphabet. This is the exact same expression. Okay. Now, that said, let's think about this dy integral. And let me make the observation that J, whatever it is a value. It doesn't depend on y. It's a number. And constant numbers, I can just toss them right inside of that dy integral, just like it's a 17. Right? Constants move in and out of integrals, no problem. Seems like a weird thing to want to do, but perfectly legal. Now, next, let's look at this integral. And let me remind you that when you have an integral inside of an integral, the variable further to the outside is a constant, and that means that I can treat this e to the negative y squared as a constant. I can toss it inside of my dx integral. And that seems like a weird thing to do, too. At this point, you might say, it looks like I've taken a hard question and I've managed to negotiate it around to being a much harder question. So it seems. Right? Now here's the slick move. The slick move is to observe that I'm apparently doing a double integral over all values of x and y. Namely, I'm doing a double integral over the entire xy plane. And if I'm doing a double integral over the entire xy plane, I can interpret that as r and theta ranging over, well, whatever values I need to sweep out the entire xy plane. All directions. Theta goes from 0 to 2 pi. And then for any given direction, all distances, 0 to infinity. It's just kind of a polar way of covering the entire plane. Now, of course, when I do that, I got to follow the rule. Dx dy is r dr d theta. And now look at what has happened. The scary integral. The r integral where the e to the negative r squared was, where, oh my gosh, this is, there's no antiderivative, etc. But all of a sudden, magically, there's an extra factor of r in there. This is an easy u substitution. Just let u equal to negative r squared, and it all just falls apart. There's nothing to it. At this point, this goes through very easily, and our answer is pi. This really, really clever. Again, I did not think of this on my own. I don't think I ever would have. But let's not spike the football on the 2-yard line, but let's not forget it was j squared that we computed that was equal to pi, so j is the square root of pi. The actual integral we wanted to know, square root of pi. And there we go. Everybody follow? It's really cool. It's a weird thing. Sometimes when you want to solve a problem, you have to start by making the problem increasingly harder. And yes, it makes the problem harder, but it also gives you access to more techniques. Right? Double integrals, we have more techniques than we do for single variable integrals. And it just happened to be that even though the problem was harder, the techniques were even better. Okay, so now we're going to move on to cylindrical coordinates. Again, you can pull back your domains, or again, you can push forward your slices, aka you can interpret, for example, your theta slices. Like there's a theta slice, constant value of theta. I can just ask, well, what does a constant value of theta look like over here in XYZ space? And there it is. Constant value of theta looks like this. Right? I like to think of this as being kind of a door on a hinge. This shape here is called a half plane. So I describe this as a half plane hinged on the z-axis. Right? The lingo. So, yeah. All right. Well, and here's what R slices look like. R slices, constant value of R is just going to be, well, a cylinder. Part of a cylinder. Okay. So we're going to do some cylindrical coordinates examples now, and a couple tips and tricks. For one thing, even though you do have 6 choices for how to order your differentials, again, asterisk for the occasional, extremely weird, rare, usually manufactured examples that to the contrary, you practically always want to put dz either just to the outside of dr d theta or to the inside of dr d theta, but you want to leave dr and d theta together and in that order. So dz on the inside or outside, everything else just like this. So not that many options. It's just 2, but you do get to choose. Again, don't forget your stretching factor. Nice little hack. Always write down your stretching factor of R as you write down your differentials. You would be surprised how easy it is to forget. And if you forget, then oh gosh, it's then I can't give you credit for it if it's not there. That's just the deal. So, really dangerous little landmine. You've been warned. So make sure to be careful about that. And then again, we identify key points and our usual process for finding bounds. So let's do one. Let's look as our domain, this upper half ball. Solid half ball there, part above the XY plane. And again, you could do this in rectangular coordinates, square roots, nightmares, horrifying, right? Nobody wants to do that. Okay, so let's write down our cylindrical differentials. I'm going to notice, by the way, I've already successfully not forgotten my stretching factor, right? Again, very nice little memory trick. So there it is. There's my R. Arbitrarily, I'm going to put the dz on the inside here. We're going to do it the other way momentarily. For the moment, let's put dz on the inside. And here we go. Theta. This is what a theta slice looks like. All right, my theta slice is this sort of quarter disc right there. Okay. And what's values of theta? Well, again, we've kind of enveloped the z-axis, and so my theta slices go all the way around, and so that means theta goes from 0 to 2 pi. Everybody happy? Okay. All right, so now we fix a value of theta. Now we look at R slices. R slices, you'll remember, are little cylinders. How does an R slice intersect our existing theta slice? Well, a little geometry. How does let's see here. How does a quarter disc like that intersect this cylinder? Well, it's just along this edge. Just that right there. So there's our R slice of our theta slice. Where do they start? Where do they end? Well, the first R slice is there, where R is pretty clearly 0. It's on the z-axis. Our last R slice is this point, which is on the edge of this half ball of radius A. And so R there is A. So we're 2/3 of the way done. Is everybody still with me? Is everybody happy? All right. And then lastly, again, focused on our R slice of our theta slice. Now, what's the range of values of z? Let me do it like this. Z. Where does z start? Well, z starts at that point right there, which is in the xy plane, where z is equal to 0. So our inner lower bound is 0. And let's see, where does z end? Z ends at that point right there, which is, now here's where we have to start really being careful. What can I say about this point here? Well, it's on the sphere. What can I say about the sphere? What do I know about the sphere? Here's the equation of a sphere. Cylindrical equation, of course, because I'm interested in cylindrical variables. And flashbacks to chapter 1. This is the equation of a sphere. And now a reminder, wait, what am I doing here? Why did I write that down? Well, because I'm looking for z bounds. And so this z right here, I got to solve for that z, and I get square root of a squared minus r squared for our upper bound. Is that good? All right. So there you go. Options. Yeah, a confession, to be fair. I mean, there is a square root in here, right? So this is not perfect, but it's fewer square roots than I would have gotten had I done this, rectangularly. I would have had a lot more square roots. So it's, better. Okay, let's try it in the other order. Notice here I'm putting dz on the outside instead of the inside. This is our other reasonable cylindrical option. So, what are we going to do about this? Well, starting with z slices. There's a z slice. Geometric appeal from the picture when you take this horizontal z slice of our of our ball. You get a little disc. First and last, well, first one is down here, where z is 0. Last one is at the North Pole, where z is a. Again, don't forget this is a disk of radius a. Alright. Now we focus on a z slice, so we're going to look at this thing right here. That z slice, what's up next? Next we are apparently looking at theta. What's my range of values of theta? Well, theta slices look kind of like this, and I think you can, that didn't work out well. Theta slices look kind of like this. And geometric appeal, I claim they go all the way around. And when it goes all the way around, 0 to 2 pi. Right. And by the way, arguably, you don't start exactly exclusively at 0. If you want to view this as, pi to 3 pi, that's fine. Right? Negative pi to positive pi, okay, that's all good too. I think all exceptions granted, all's being equal, I think the easy way is to go 0 to 2 pi because I like 0. Right? Get a free 0. Okay. And now, looking at a particular theta slice of our particular z slice, now we want to know the range of values of r, and the starting value of r is, well, it's that point right there, which is clearly 0. Right, and the ending value of r is going to be at that point right there. Okay, what can I say about that point? That point is on our sphere, which has this equation. Again, same exact equation as the previous example, but careful. Recall, we're looking for an r bound. So in this equation, we're not solving for z like we did before. Here, we're looking for an r bound, so we solve for r. And that gives us this as our r bound. Everybody all right? Okay, so that's cylindrical. And now on to spherical. Again, same basic strategy. Change of variables, push forward the slices, all that same stuff. This is what the slices look like. This is just kind of a matter of thinking it through geometrically, but a constant value of theta, just like before, is a half plane hinged on the z-axis. They start to get weirder from here. It's going to turn out not really to matter that much, but here's a phi slice. Right, a constant value of phi, of course, is a cone. Right, you may recall from examples that we did back in chapter 1. And then constant value of rho is a sphere. So kind of weird looking slices. Good news, you're not going to have to think very much in terms of these weird shaped slices, because as it turns out, here's the best choice. You should practically always, just to streamline things, I'm going to say always go in this order, d rho, d phi, d theta. So we're always going to be doing theta slices, which are half planes, hinged on the z-axis. That's easy. We'll then not have to look at the entire phi slice. We'll just be doing phi slices of just the theta slices, not the whole phi slice, and then etc. And it's going to turn out that this makes everything work out really well. This, again, always best, asterisk, but as far as we're concerned, always go in that order. And again, please, please, please don't forget your stretching factor. Again, a really good hack for remembering it is to write this down all at once together. Don't ever write down d rho, d phi, d theta by itself. There's no reason to, ever. You should always write rho squared sine phi, d rho, d phi, d theta all at once, right? Practice saying that so that it just seems like a natural thing to write down. And again, you should get the willies anytime you find yourself writing down just d rho, d phi, d theta by itself. It's not really a thing. Okay? This whole thing together is the thing. Okay, all right, so we're going to draw the line right here, and we'll pick up here on Friday. Y'all have a good one. See you later.